Hello everyone. In the previous clip, we saw the method to find a time period of SHM of simple pendulum, and there we used the concept of restoring torque. And the situation was something like this: that we have a pendulum of mass m. What we did is we displaced it through a very small angular displacement, that is theta. This theta was very small, and so what we found as was that ultimately this was oscillating. So what was responsible for bringing this bob back to its mean position? That was a restoring torque. So there we used the formula of torque, that is I alpha and all, and we found out. Now we will use the same method, but the only difference is here we will talk about this displacement, that is x. Means we 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 held this bob, we just displaced it a little bit, and this theta is very small, so this x will be also very small. So what this x will be, this is your L, this x will be L theta. I hope you get this concept. I'm explaining you. Suppose you have a circle, you have this, you have to find the length of this arc. Suppose this arc, so I take it as L. You have this theta, you have the radius as r, so this L comes out to be r theta. That is what I have used here. This length of the arc, that is x, will be is equal to L into theta. So this is what I'm using. So now when we consider this diagram, we have this mass, we have displaced it a bit. This displacement is very small. I'm drawing it for my convenience of diagram. So you have this m, this is your theta. You have a force, that is mg, acting downwards. You have one force acting along the thread, that is string, one perpendicular to it. When you extend it, you get it to be theta, alternate interior. This turns out to be theta, vertically opposite. This comes out to be mg cos theta, and this is your mg sin theta. Now there we were talking about the torque that was due to this force. Here we will not talk about torque. Here we will talk about force restoring. So this force restoring is this force is along the thread. It is only increasing the tension. It is not helping this bob in coming back to its mean position. So this force is responsible for bringing this bob back to its mean position. So the force restoring is mg sine of theta. So this force restoring, we can write it as mass into acceleration restoring is equal to mg sine of theta. Mm gets cancelled. We have this acceleration restoring as g sine theta. So as we have assumed this theta to be very small, we know this approximation, that when theta is very small, sine of theta is nearly equal to tan of theta is nearly equal to theta. So we will use this approximation here, and we will write it as AR is equal to, that is acceleration restoring, is equal to g of theta. So earlier we had written that length of this arc x is equal to L theta. So this theta is going to be x by L. So this theta we are replacing here. So we can write this theta as x by L. So it comes out to be this. So from the funda of SHM, we know that acceleration should be directly proportional to x. A comes out to be omega square x. Here it is a minus, but when we talk about mod, we have omega square x. So now we can write this acceleration restoring as omega square x is equal to g by L times of x. This x gets cancelled. Omega comes out to be under root of g by L. Your omega is 2 pi by t. It is g by L. So your t comes out to be 2 pi under root of g by L. So by this method also, in this method we did not use the concept of torque, that is restoring torque. We used the concept of restoring force. We did not bring about brought rotational motion into consideration. We just brought force and we considered a small displacement x and we brought this result. Thank you very much.